All right, so we talked about followers. In case it wasn't clear, everything we saw so far has been a follower, except wait, wait's somewhat special. It's not really a follower, but lerp follow or lerp transform set. Those have all been followers because those have all been follower animations because the follower follows to the iterator. Makes sense, right? Oops. Okay, so we just saw the rotated example. That was the first thing we saw in lerp. But we also noticed that it's somewhat awkward because we had to do that rotated zero, right? We had to do this rotated zero, which is somewhat awkward, especially if you're doing this a lot. And a crucial idea about modern code is that we have boilerplate, we have, okay, I mean, I wouldn't call this complex logic, but if we have annoying logic, we want to abstract that out and not have to worry about it. So this is where progressors come in, is that they're similar to followers, but they do have slight differences. And principally, the idea with progressors is that it's going to take in an iterator and it'll do modifications to it. So let's contrast that with followers. With followers, all the modifications I would do myself, and then I would ask the animation to follow. The animation would make no changes to the iterator, right? Animation might make changes to the follower, but it would make no changes to the iterator. On the other hand, progressors will make changes to the iterator, they will make changes to the follower, but they'll also make changes to the iterator. So let's actually take a look at this example. So over here, I defined a progressor that's going to abstract away that common boilerplate of rotation. Okay, so it's going to abstract away that common repeated logic and say, hey, you don't have to worry about handling the mesh equals rotated mesh rotation 0 yourself. I'll do that for you. So not only will I make it so that the follower goes to the final iterator state, I'll even handle the logic of changing the iterator. So that's what we can see here, right? Is that the mesh is being changed, and then we linearly interpolate the rotation factor, and then it basically did it. So this is literally no different than if we did this ourselves, right? If we did the lerps equals rotated of lerps rotation 0 and then mesh dot rotation equals rotation, it would be no different than having this rotate function. The benefit of the rotate function is that we only have to do this once, and I don't have to worry about typing it out myself. Okay, so one thing I will say though, let's actually just take a look at this just so that we can make sure it works. Right? And then it rotates it for us. The one thing that we have to be careful with progressors, so they are nice, they're very nice, they're very easy to call, but the thing we have to be careful is that it modifies the input. So it might be unexpected that at this time, the lerps variable was changed. It was changed, and in fact, it's no longer of type square anymore, it's of type rotated, because it was changed by this progressor. So that's one thing you definitely do have to be careful for. But they are convenient because it abstracts common logic away. Okay, so as an exercise, let's see if we can use this pattern and create shift and scale progressors. Okay, another common example is hiding. So it's very, very common to basically do something like this where you say mesh equals the empty set and then fade to the empty set, which equivalently is just a fade out operation. And we do it so much that we might as well just create this fade out operation. But again, the thing to be careful is that it's going to modify the input iterator, which is what makes it a progressor. Alright, that's actually it about progressors. Just make sure that you're careful about knowing that it modifies the input iterator. But other than that, it can abstract away common logic.